Gazing up at the night sky, even with the naked eye, one cannot help but be overwhelmed by the tapestry of stars and constellations visible in the heavens above. The prominent band of the Milky Way stitches across the sky, containing more stars than could ever be counted. Yet what we see represents only an infinitesimal fraction of the hundreds of billions of stars that make up our galaxy. And the Milky Way itself stands as but one galaxy among at least 2 trillion others that sprinkle the far depths of space as far as our telescopes can observe. So much cosmic real estate lies just beyond our home solar system, waiting to be explored. Venturing out beyond the domains of our sun's influence reveals an exceedingly grandiose stage, both beautiful and perilous. Our solar system occupies the inner suburb of the Milky Way galaxy, approximately 25,000 light-years from the brilliant core. The Sun and its family of planets, moons, asteroids, and comets are embedded in the Orion Arm, a tendril of gas and stars spiraling out from the galactic center. Seen edge-on, the Milky Way would appear as a thin, luminous disk approximately 100,000 light-years across, with a bulging core tipped by bar-like structures that may harbor a supermassive black hole at the center. Yet even our Orion Arm neighborhood proves sparsely populated, with an average separation between stars of about 5 light-years. Proxima Centauri, the nearest star at just over 4 light-years away, is still 250,000 times more distant than Earth's separation from the Sun. Such vast intervals demonstrate the challenging scales involved in any voyage beyond our system. But these spaces between the stars also offer essentially unlimited real estate to someday support colonization efforts by civilizations advanced enough to traverse the gulfs. Several dozen stellar systems congregate around our own within a radius of about 50 light-years, forming a local bubble. Neighbors include bright stars like Alpha Centauri, Sirius, and Procyon, along with binary pairs and red dwarf systems. Some may possess their own families of planets, though none confirmed thus far appear hospitable to life as we know it. But venturing just a bit farther, to approximately 80 light-years, brings us to the exciting Tau-Ceti system that may harbor at least 2 worlds in the habitable zone. This nearby interstellar neighborhood offers a convenient starting point for a budding spacefaring civilization like our own to stretch its wings. In a galactic sense, we occupy the stellar suburbs surrounded mostly by older yellow stars and red dwarfs. The density of systems increases toward the Milky Way's core, with many massive young stars cloistered in clusters and nebulae. One goal for probes sent outside our system may be to study these stellar nurseries and observe new planetary systems coalescing. One especially rich target is the Orion Nebula, situated about 1,500 light-years away along one of the galaxy's spiral arms. Illuminated by blazing massive stars, this nebula contains enough raw material to forge over 10,000 stars resembling our Sun. Infrared telescopes can peer through its clouds to watch protoplanetary disks take shape around newborn stars. What secrets might we learn about our own origins by dispatching probes to listen in on the formation stories of other worlds? Beyond the orb of neighboring stars, the geography of the wider Milky Way comes into focus. We reside approximately 25,000 light-years from the galactic center, embedded in the Orion Arm, one of several major spiral arms winding out from the core. It takes roughly 230 million years for the solar system to complete one orbit around the galactic center as we slowly bob up and down across the equatorial plane. This oscillation ranges about 150 light-years above or below the plane every 62 million years. Currently, we find ourselves fortuitously in a cleared-out low-density cavity below the plane called the local bubble. Formed by past supernovae, this region has a lower density interstellar medium that reduces hazards from gas, dust, and radiation compared to much busier galactic neighborhoods. Future spacefarers venturing beyond 20 light-years will want to time their travels to stay within stellar bubbles and avoid the chaotic spiral arms. Navigating through the galaxy's outer disk and beyond promises fantastic sights, but also great peril. Pockets are rife with hazards like radiation, gas clouds, and wandering rogue planets ejected from ravaged solar systems. But structured vectors like spiral arms create useful pathways between oases, and sufficient radiation shielding and deflectors can mitigate many risks, allowing travelers to hop between interstellar bubbles. What wonders might patient explorers uncover over generations spent roaming the Milky Way? Perhaps even encounters with alien civilizations also plying these cosmic trade routes. The center of the galaxy holds special allure, with immense crowds of stars orbiting tightly around the hypothesized 4 million solar mass black hole called Sagittarius A. About 10% of the galaxy's stars reside here in a luminous sphere about 10,000 light-years across. Bathed in the infrared glow from vast amounts of interstellar dust, this energetic core region offers extreme conditions but also unique windows into astrophysical and cosmological mysteries. To visit its bustling heart would be to commune with the essence of our galaxy. Beyond the main disk, the Milky Way's halo stretches 500,000 light-years and contains over 100 ancient globular clusters swarming with millions of elderly stars. And farther still, an enormous dark matter halo perhaps 10 times larger envelops the luminous galaxy, its mass gravitationally shepherding the cosmic island we call home. What adventures through the outskirts and fringes of our galaxy might reveal its full structural secrets. Yet for all the Milky Way's splendor and immensity to our limited human perceptions, it amounts to but one grain in a universe teeming with billions of other galaxies. Were we to voyage 2.5 million light-years toward the Andromeda Galaxy, we would reach our nearest large galactic neighbor, where hundreds of billions of stars await. Just one step beyond our own stellar metropolis lies a whole cosmopolitan landscape to lose ourselves in. The known universe extends over 90 billion light-years across, populated by galaxies numbering in the trillions, grouped into enormous clusters and superclusters. Every new observation further expands the reach of the observable horizon, unveiling ever more alien vistas. The cosmos seems without end, larger and more magnificent than we can presently comprehend. What remarkable discoveries await out there among such grand celestial cities, across the galaxies, beyond the places where even our mighty telescopes cannot see? The heavens beckon, filled with profound mysteries, and surely wonders beyond imagination. Situated a mere 25,000 light-years from the brilliant core of the Milky Way galaxy, our familiar solar system occupies a quiet suburban lane in the grand spiral metropolis that is our cosmic home. Yet even here in the galactic boondocks, an eclectic array of stellar systems congregates in the neighborhood around our Sun. Within a radius of about 50 light-years, a few dozen stars coalesce into a local bubble, forming a stellar island in the vast interstellar seas. These nearby systems offer our first destinations when the day comes that humanity is ready to voyage beyond our own planetary doorstep. The nearest celestial haven is the famous binary pair Alpha Centauri at just over 4 light-years away. This two-star waltz features a fiery yellow sun-like star, Alpha Centauri A, in orbital dance with the dimmer orange dwarf star Alpha Centauri B, a third stellar interloper. The diminutive red dwarf star Proxima Centauri orbits the main pair at a farther distance. Proxima holds the distinction of being the single closest star to our solar system. At a hair's breadth over 4 light-years, it offers a tempting first port for future interstellar travelers. Other notable stellar residents within 10 light-years include Barnard's star, a low-mass red dwarf ambling just 6 light-years away. and the binary brown dwarfs Lumen 16 at around 6.5 light-years. Wolf 359, another pedestrian red dwarf plodding along at 7.8 light-years out, has the distinction of hosting one of the lowest mass stars known. These tranquil, lightweight neighbors present relatively easy hops for space probes centuries from now. Their subtle magnetospheres and gentle stellar winds pose limited radiation threats as well. The next ring of systems extending from 10 to 25 light-years away includes more spirited stars. Epsilon Eridani, at just over 10 light-years, sports an extensive debris disk and possible Jupiter mass exoplanet ideal for further study. The bright three-star system Alpha Centauri reigns at 11.3 light-years, while orange giant Layton's star Moses at 12.4. Groombridge 34 resides at 15.6 light-years, among the earliest M-class red dwarfs detected, and iconic Sirius sparkles at only 8.6 light-years, despite being the fifth nearest. Its brilliant white sheen should render it a visible beacon from many interstellar vantages. At approximately 25 light-years, luminaries like the Sun's weird twin Epsilon Indi and the rapid rotator Procyon contribute notable diversity. Beta Hydri and Rho Eridani add southern sky representation to the catalog of nearby stars, along with orange giant Delta Pavonis. Sigma Draconis stands out as well for its pole star-like orientation above Earth's sky. Together, these adjacent stars help benchmark the first feats of interstellar travel, offering waypoints and potential destinations less intrepid explorers may settle for. The more adventurous can use them as mere stepping stones deeper into the Milky Way. Leaping past 25 light-years, the thickness of the local stellar precinct starts to diminish, but gems continue to glitter out to 50 light-years and slightly beyond. Here resides the renowned binary Alpha Centauri triple system at 25.4 light-years, whose planet-hosting member Proxima offers the closest possibly habitable world beyond our solar clan. The bright primary pair present unique dynamics for study from such short range. Stellar twin Tau Ceti, with its own tantalizing planetary candidates, loiters at 26.7 light-years. Epsilon Indi, a brown dwarf cousin to the Sun, hangs out at 27.3 light-years away. Quirky binaries like UV Ceti provide flare star curiosities. L757-51 is in sedate red dwarf-white dwarf pair for contrasting around 29 light-years out. There is even an entire 5-star system known as WISE 1049-5319 nestled at 31 light-years away, adding still more variety to neighborhood's stellar census. And many other solo stars, doubles, and multiples sprinkle through this volume, surrounding humanity's first interstellar sandbox. Together, this congregation of perhaps a few dozen stellar inhabitants forms the basic landscape for the initial stage of interstellar emergence. Each individual system will have unique traits to offer the spacefaring humans or artificial intelligences that come to visit them up close via compact probes. Eventually, even swift interstellar arcs capable of supporting the frail wetware of biological explorers might traverse between some of the nearer targets. Even our first fumbling experiments may uncover profound insights. The nearest stars hold so many secrets and wonders waiting to be unfolded. Inevitably, pioneers will yearn to venture beyond these initial haunts. Using various propulsion schemes, they can follow tendrils of stars and nebulae deeper through the Orion spur, voyage toward the shimmering core, or perhaps attempt an expedition to a globular cluster's densely packed worlds. The very first interstellar travelers will be the trailblazers of an immense cosmic frontier. As their records filter back via communication laser, each new system revealed will enlarge humanity's conception of our native stellar ecosystem nestled amid the great Milky Way. Standing hopefully at the dawn of such epochal ages of exploration, our very limited sense of what lies beyond our present solar limits ensures boundless surprises await out in that wilderness of stars. The nearest suns hold so much promise for advancing human and transhuman minds. Each incremental step outward will feed an intoxicating sense of gradual mastery over the interstellar environment. In astronomy's continued quest to survey ever more distant realms, we must not lose our sense of wonder for the local bubble that is our intimate celestial home, where gentle stellar currents now nudge humanity's sails toward the waiting sea of stars. Among the most visually spectacular and scientifically informative sights the cosmos has to offer, stellar nurseries provide a window into the dawn of star and planet formation. These vast, glowing nebulae of gas and dust cradle newly ignited stars emerging from their natal cocoons. Intense radiation and stellar winds sculpt fantastical shapes and structures within the cosmic incubators. Journeying to examine these stellar hatcheries up close promises invaluable insights into the story of our own Sun and solar system's beginnings over 4.5 billion years ago. Situated approximately 1,500 light-years from Earth lies the Orion Nebula, the nearest and most prominent stellar nursery visible in our night sky. This emission nebula shines by reflected starlight from the massive, young stars gestating within. Towering some 24 light-years across, its hydrogen clouds hold enough material to churn out 10,000 stars the size of our Sun. The fierce stellar winds and intense ultraviolet radiation from its newest brood of giant stars energize the nebula's eerie glow. Four monstrously hot, blue supergiant stars, collectively called the trapezium, illuminate and sculpt the Orion Nebula's central regions. Their surface temperatures exceed 30,000 degrees Celsius compared to the Sun's tepid 5,500. Around these luminaries, the nebula's contents are constantly shaped and reworked, triggering a cascade of new star formation. Intricately sculpted folds, filaments, and cavities hint at the dramatic interactions between stellar radiation and magnetic fields within Orion's tumultuous interior. Yet over 100 times more distant at 7,000 light-years lies the iconic Eagle Nebula, known for its visually stunning pillars of creation, imaged by the Hubble Space Telescope. Here in the Serpens constellation, furious radiation pressure from energetic young stars is slowly eroding away the towering molecular pillars from which new stellar offspring are birthed. Ghostly federations of fledgling low-mass stars, still wrapped in their dusty cocoons, stud the towering columns. The entire nebula spans some 70 by 55 light-years. Though far smaller than Orion, within the heart of the Eagle Nebula lies a remarkably productive stellar factory known as NGC 6611. Containing at least 460 confirmed young stars, it is one of the most active star-forming regions in our galaxy. Fueled by ample reservoirs of cold molecular hydrogen, stellar birth rates in NGC 6611 exceed our entire Milky Way galaxy. Churning out massive stars up to 60 times the mass of our Sun, NGC 6611's prodigious output impacts the entire Eagle Nebula's evolution. The Orion Nebula, Eagle Nebula, and similar stellar nurseries allow astronomers to study the various phases of star formation in action. Within these cosmic creches, the cycle begins as an immense cold molecular cloud core starts to gravitationally collapse. Density dramatically increases in the center, as conservation of angular momentum causes the cloud to flatten into a rotating protoplanetary disk surrounding the nascent protostar. Gas continues raining down onto the stellar embryo from the surrounding envelope. Next, fierce stellar winds from the newborn star help disperse leftover disks of material, exposing it directly to view in visible and infrared light. Jets of accelerated ionized particles emerge perpendicular to the disks, spewing material into space. Over its lifespan, the youthful star will contract and heat up as hydrogen fusion slowly commences in its core. After around 30 million years, the star joins the main sequence as our Sun did 4.5 billion years ago. Surrounding infant stars, protoplanetary disks just light years across contain enough material to build an entire planetary system. Beyond Earth and the other worlds orbiting our middle-aged Sun, we have now directly imaged over 1,000 of these planet-forming disks in facilities like the Subaru Telescope and ALMA Observatory. As well as studying other solar systems architectures, observing these rotating planet factories helps establish the timeline for planet formation and emergence of habitable conditions. By traveling to a stellar nursery, an advanced probe could make close-range observations to study stellar evolution and planet construction in action. Passing near dense clumps of gas, it could take samples revealing environmental composition, temperature, ionization levels, and motion. High-resolution imaging of protoplanetary disks would illuminate planetary formation and morphology with unparalleled depth. And examining primordial solar systems could tell us if our own Sun and planets developed through typical or atypical processes billions of years ago. Mapping magnetic fields around nebulae and within stellar nurseries also helps explain how stars form. Magnetic forces help regulate gas cloud fragmentation, protostellar disk shapes, and filamentary structure inside nebulae. Young stars show enhanced magnetic activity and flaring, generating formidable X-ray radiation. Their energetic outflows and jets of stellar material trace along magnetic flux lines. Even star formation rates may correlate to magnetic field strength in molecular clouds. A probe that could carefully measure field directions and strength around nebulae would provide data to test magnetically driven star formation models. Stellar nurseries further offer clues to illuminating cosmological mysteries. Because their embryonic stars have low metallicity, abundance measurements can shed light on early galactic nucleosynthesis after the Big Bang. Observing conditions right after the first stars formed may reveal more about the universe's transition from darkness to light. And densities within nebulae make them ideal laboratories to seek out exotic theoretical particles like axons that could compose dark matter. Some even hypothesize black holes may commonly spawn within dense nurseries. Exploring stellar hatcheries promises a journey both visually spellbinding and scientifically invaluable. To sail by glowing towers of nebular gas light years in height, illuminated by the searing blaze of massive newborn stars, would be to experience these regions as never before. And insights gathered into the mechanics of starbirth and formation may well help complete the galactic story of our own Sun and worlds. To kneel before the pillar stars in Orion or spread of eagle wings in Serpens is to make sacred pilgrimage to the birthplaces of worlds. Among the celestial jewels that glisten across the firmament, nothing captivates human curiosity more than the stars. These cosmic lighthouses shine as brilliant beacons in the darkness, their fires fueled by thermonuclear reactions within. Yet stars display a remarkable diversity in their attributes and life cycles, showcasing the full splendor the universe has to offer. A grand tour across our home galaxy presents opportunities to encounter stellar varieties ranging from dim red dwarfs to titanic hypergeans millions of times more luminous than our Sun. At the diminutive end, red dwarf stars constitute nearly 75% of all stars in the Milky Way galaxy. Although fairly faint, their incredible ubiquity results from their low mass and miserly fuel consumption, allowing lifespans up to 1 trillion years. Proxima Centauri, the nearest star at 4.2 light-years, typifies these petite, ruddy suns. Burning hydrogen so methodically through convection, some red dwarfs may persist since the earliest epochs after the Big Bang. Planets orbiting within their snug habitable zones could experience perpetual twilight under hair-thin crimson skies. Slightly more massive stars along the main sequence, like Earth's own Sun, shine yellow-white for 15 to 20 billion years by fusing hydrogen into helium within their cores. Our middle-aged sun formed 5 billion years ago, and still has 5 billion more before swelling into a bloated red giant. Main sequence stars support the emergence of life as we know it. Future technological civilizations may harvest their energy using orbital megastructures like Dyson spheres or swarms of solar collectors. At the upper end of main sequence stars, blazing blue-white beacons 7 to 20 times the sun's mass fuse hydrogen furiously over lifetimes of tens of millions of years. Sirius, the brightest star visible from Earth at 9 light-years away, falls into this category. Rotating at breakneck speed, massive stars forge heavy elements in their seething cores to scatter about the galaxy when they detonate as brilliant supernovae. Any worlds orbiting massive stars contend with intense ultraviolet radiation, searing stellar winds, and peril from premature stellar death. Yet even the largest main sequence stars only scratch the surface of stellar scale and luminosity. Next come blue hypergiants, shimmering up to 50 times more massive than the Sun, and hundreds of thousands of times more luminous. Scorching over 40,000 degrees, these ephemeral colossi lead hard, fast lives of only a few million years. Their prodigious light output rips away outer layers of gas, which become visible as gossamer veils and flares. Hypergiants will end their stellar journeys as extraordinarily energetic supernovae. The most titanic stars of all are the red supergiants, swelling to the size of Jupiter's entire orbit, around 5 billion miles across. Betelgeuse, noticeable as the reddish shoulder star of Orion, is a red supergiant variable hundreds of times the Sun's diameter. Despite their cool surface temperatures of under 4,000 degrees, red supergiants emit tremendous luminosity thanks to their immense surface area. After just 1 to 20 million years, they too exhaust their nuclear fuel and erupt in epic supernova, leaving behind exotic remnants like neutron stars or black holes. After the catastrophic drama of death or near death from massive stars, smaller stars' endings unfold more gently. As main sequence suns like our own exhaust hydrogen, they swell hugely into red giants over billions of years. Cool and bloated red giants may expand beyond the orbit of Mars as they eventually shed their outer layers, exposing the shrunken dying ember called a white dwarf at the center. White dwarfs themselves very slowly fade to black over untold eons. Denser than any substance on Earth, white dwarfs pack the mass of our Sun into the volume of Earth. Supported by electron degeneracy pressure, these crystalline spheres glow from residual thermal heat. Earth-sized diamond crystal shards, white dwarfs eventually turn dark once their temperatures ebb over hundreds of billions of years. Leftover white dwarfs add their own unique sparkle to the heavens. At the opposite extreme, catastrophically compressed remnants called neutron stars manifest when stars from 10 to 30 times the Sun's mass meet their demise. Compressing an entire star's worth of material into a sphere only 10 miles across, neutron stars spin rapidly as pulsars while emitting powerful lighthouse beams of radiation. Their densities exceed an atomic nucleus, giving rise to exotic matter found nowhere else. Some neutron stars warp spacetime itself in their vicinity. Rarer still, a handful of solitary stars seemingly missing from galactic surveys could in fact be elite stellar remnants called black holes. When the most massive stars 25 times larger than the Sun perish, they may leave behind completely collapsed objects so steeped in gravity not even light can escape. Intense tidal forces would shred any substance, spiraling into their singularities. Supermassive black holes up to billions of solar masses dwell at the hearts of galaxies, but solitary stellar black holes stealthily roam interstellar space. This menagerie represents but a sample of stars' full zoology. Within each category exist manifold unique formations like binary pairs, red dwarf variability, recurrent novas, white dwarf crystallization, neutron star glitches, and microcosar black holes. Astronomers continue identifying newfound stellar species like brown dwarfs and magnetars. Our own Sun, an ordinary middle-aged yellow dwarf, may one day be seen as utterly pedestrian. Mapping the stellar canvas rewards us with insight into stars as both individuals and populations. The constitution and history of stars underpins the evolution of galaxies. Stellar composition directs what planetary systems may arise around them, and the resulting chemistry produced in their cores, reprocessed through the cataclysms of supernova, shapes the very molecules required for biology. Our civilizations owe their existence to myriad generations of stellar alchemists. Studying stars across our galaxy and beyond illuminates all creation's connectedness and continuity. The heavy elements in our veins were forged untold eons ago within ancient stars. The calcium in your bones once coursed through the nuclear heart of a massive star that expired in a terrible blaze before our solar system was born. And 5 billion years hence, the atoms that currently make up planet Earth may voyage forever outward aboard stellar winds to someday help compose new worlds. From twinkling points of light that guided ancient mariners to other suns that may host their own living worlds, stars embody the cosmos' abiding mysteries. Contemplating the lives and deaths of stars grants deeper appreciation of our true place and purpose in the universe. All cultures and beings are insignificant without the web of stars stretching across the great beyond. Yet stars also connect us through the eons. Gazing up at their shining forms, humanity realizes its journey's endlessness. We merely borrow their light for a time. Rogue planets, also known as nomad worlds or interstellar planets, are planetary mass objects that do not orbit any star. They float freely through interstellar space. It was previously thought that planetary formation only occurred within protoplanetary disks around young stars. However, it is now known that some planets can be ejected from their original planetary system and become what are called rogue or interstellar planets. Rogue planets are thought to form in much the same way as normal planets, from accretion of dust and gas within a protoplanetary disk. However, differences in mass between growing protoplanets can lead to gravitational interactions that eject some protoplanets from their systems entirely, sending them out into eternal wandering of the dark abyss between the stars. Indeed, ejection is considered a likely outcome of planet formation. For each planet that successfully forms in orbit around a star, it is estimated that 2 or 3 may be cast out as rogues to ply an interstellar course. The detection of even a few of these nomadic worlds would suggest that rogue planets are a substantial population in the Milky Way galaxy, perhaps outweighing the number of stars themselves. Just like normal exoplanets, rogue planets would come in various sizes and compositions, ranging from terrestrial rocky worlds to gas giants many times the size of Jupiter. Low-mass rogue planets, presumably dominated of rock and ice, would be relatively cool, while more massive gas giants would retain primordial heat from their formation and maintain interior temperatures warm enough to support liquid water oceans under their dense atmospheres. The detectable properties of rogue planets depend on their masses, ages, and compositions. Without starlight to illuminate them directly, rogue planets would be enormously difficult to spot from Earth. However, radio emissions from magnetic fields interacting with the interstellar medium or infrared radiation from internal warmth may reveal some wandering worlds' otherwise invisible passage through the galaxy. More massive rogue planets, giant in size, would possess densities high enough to retain primordial heat through Kelvin-Helmholtz contraction for periods of many billions of years since originating in a protoplanetary accretion disk. Such nomad giant worlds drifting endlessly through the dark oceans between the Milky Way's countless stars could support liquid water and possibly even the simplest forms of microbial life protected deep below dense atmospheres. While isolated from any fixed point of light in the black immensities, separating them from the nearest stellar nurseries, certain rogue giants may not lose warmth quickly enough to freeze at their cores. This has stimulated speculation concerning their capacity to incubate and shield rudimentary biospheres. Of course, evolution on a rogue planet proceeding completely removed from photic energy appears unlikely to generate anything resembling higher complexity biology. But even terrestrial-sized rogue planets far smaller could potentially support life through internal radioactive heating alone during their early years, before cooling sets in as uranium, thorium, and potassium isotopes in their rocky interiors underwent decay. As long as interior temperatures remain high enough for liquid water to exist under high pressures deep below any surface ice sheets, simple microbes may have found habitable zones within rogue worlds prior to their fading thermal budgets, constraining all near-surface water to solid form. Whether life from prior planetary systems was ejected on rocky rogues and survived in these narrow subterranean refugia to seed other starbirth regions remains unknown. But the possibility underscores how readily and unexpectedly life might spread via mechanisms natural yet still hidden from our view. The isolation of rogue planets makes their discovery exceedingly challenging. Without the light from a host star, rogue planets cannot be directly imaged. The best methods for detecting them are subtle clues such as microlensing, which looks for the brief brightening of background stars caused by the gravitational lens effect of an intervening rogue planet. Although gravitational microlensing has revealed some candidate free-floating planets, their isolation precludes spectral analysis to characterize their atmospheres and surfaces. Alternative detection techniques rely on spying infrared radiation from rogue planets themselves, which could reveal signs of residual warmth from formation, or detecting radio emissions generated by interactions between magnetic fields and the interstellar medium. However, both methods are hindered by the faintness of signals from objects so distant and alone. A small number of rogue planet candidates have been reported based on microlensing surveys that scan the sky for signs of brief brightening caused when an object passes in front of a more distant star. However, confirming any as bona fide rogue planets requires follow-up observations to rule out more conventional explanations, such as background stars or brown dwarfs aligned by chance. Additional candidates have been identified by observing infrared signatures thought unlikely to arise from hypothetical small stars or brown dwarfs in similar age stellar nurseries. Their isolation supports classifying them as rogue planets, but establishing this definitively remains challenging without a host star for context or precise mass measurements. Direct imaging, which can resolutely distinguish rogue planets from stars or brown dwarfs, could confirm candidates if instruments grow sensitive enough. But that lies far beyond current abilities. Statistical arguments suggest the population of rogue planets in our Milky Way alone may number in the billions or trillions, dwarfing the tally of stars or even planets bound to stars. Various studies estimate that for every star with planets, there exists anywhere from 2 to 5 orphan planets cast out of their natal systems. Simulations of early planetary formation point to ejections as an inevitable outcome of the gravitational chaos when multiple growing protoplanets interact before systems settle down. In very active and dense newborn star clusters particularly, the chance of a forming planet suffering a close encounter that ejects it from the potential well of its star is high. Observational evidence lends credence to the expectation that most planets form not in placid orbits, but amidst the hellish turbulence of new starbirth. Rogue worlds likely represent the largest single population of objects in our home galaxy by far. How could such vast numbers of nomad planets have gone unnoticed until now if they truly drift in such profusion? The biggest issue lies in detecting them at all without the light of a host star. Even the closest rogue planets to us would appear unfathomably faint and inconspicuous against the backdrop glow of countless more distant solar systems. They elude the notice even of our most powerful telescopes, peering to the edge of the observable universe. Additional issues compound difficulties locating these dark drifters. Without knowing any orbital elements, searchers must canvass the entire sky randomly, hoping for a rare close approach. Their motions against more distant reference like background stars also average out lensing effects over long terms, washing out chances to spot their intermittent focus effects. It remains an extreme challenge to pick just a solitary rogue world from the sea of fainter objects filling our galactic neighborhood. Directly imaging hypothetical rogue planets seems for now an impossible feat. Even the best planet-finding instruments lose any planet's glimmer against the relentless glare of its host sun. Without a star nearby to favorably illuminate potential worlds adrift in lonely blackness, hope remains to only glimpse indirect fingerprints of their passing through subtle signs. While microlensing and infrared hints point to some candidates, finding robust confirmations prove trying. Meanwhile, continued improvements offer means to one day truly unveil these elusive nomad worlds. Future space telescopes with mirrors larger than any before and adaptive techniques to cancel out starlight may finally glimpse a rogue planet through its own dim incandescence. Advancing microlensing surveys searching more of the sky more often also bear promise to catch rare magnifying events. With confirmation of just one rogue planet definitively through direct imaging or other evidence, a new realm of discovery will open regarding these wanderers between the stars. The long-term prospects of life taking hold and evolving upon a rogue planet seem slim given their lack of a host star to nurture surface biospheres with energy and moderate climates. However, certain types of rogue planets could potentially allow life to persist for lengthy periods during their early histories when interior radioactive decay or residual heat from formation still provided refuge for subterranean microbial communities. Water presumably would have been abundant during the formative epochs of all planetary bodies as they accreted within natal circumstellar disks. Habitable conditions deep underground on some early terrestrial rogue planets may have allowed simple life forms to subsist long enough to seed other star-forming regions if ejected intact. Whether any microbes could survive century-long interstellar journeys remains unknown, yet transferring life via rock ejected between planetary systems appears broadly plausible on astronomical timescales. More viable could be the prospect of primitive lithotroughs eking out metabolisms at rare hydrothermal seeps along fault zones, accessing rogue planets' lingering primordial warmth buried far below frigid surfaces. Some diversity of subsurface microbial niches across vast ranges of pressure and chemistry seem imaginable on certain types of rogues for hundreds of millions of years. Over such protracted spans, opportunities may exist for simple evolutionary radiations to occur. However, the enormous spans between stars ensures limitations and selection pressures profoundly divergent from habitats tied to stars. Energy constraints and isolation seem sure to restrict complexity compared to illuminated stellar worlds where solar radiance drives richness. Still, subterranean microbial communities persisting in isolation throughout solar systems' eons-long trips between spiral arms represent an intriguing vision of what life well beyond our familiar conception might entail. For largest rogue planets especially, their primordial heat signatures suggest potential haven for rudimentary living systems sheltering deep inside gas giants even today, countless light years removed from mantle clouds and retaining vestiges of formation temperatures warm enough to melt silicates. The concept of empty space between stars has long been challenged as astronomers have come to realize that stellar nurseries and galaxies are filled with a tenuous yet significant constituent called the interstellar medium. This ubiquitous material pervading the observed universe is composed of gas in ionized, atomic, and molecular forms along with dust grains condensing from heavier elements. Despite its low densities ranging from a single ion per cubic centimeter in quiet zones to tens of ions in nebulae, the interstellar medium mediates processes impacting stellar evolution galaxy formation, and opportunities for planets to emerge. While long dismissed as a perfect vacuum due to the sparse densities involved, careful observations revealed spectral lines originating from ionized atoms obscuring the stars beyond. The light scattered off interstellar matter was first detected almost 200 years ago and confirmed the presence of transparent material between the stars. Later work employing spectroscopy untangled specific chemical makeup, showing the gas predominantly consists of hydrogen and helium, along with heavier molecules tracing origins to stellar nurseries and the explosive deaths of massive stars in supernova. Today, sophisticated telescopes observe intricate filaments, clouds, and pillars of material sculpted by intense stellar radiation and outflows into fantastic shapes against starfields. Over the eons, the interstellar medium undergoes birth as stars arise from contracting knots within nebulous clouds, collapsing under their own gravity. Within these incubators, new suns form from initial cores reaching fusion ignition, while leftover dust and molecular gas disperse back outwards, mixing chemistries witnessed in nascent planetary systems. Violent deaths also enrich the interstellar medium as massive stars explode in spectacular brilliance. Their fury expels intricate layers formed during nuclear burning processes, as elements heavier than hydrogen and helium and dust forged in their furnaces to drift throughout surrounding space. Slower stellar winds from cooler aging stars additionally contribute material over lifetimes measured in billions of years. Through time, the components within the interstellar medium exist dynamic equilibrium, with gas transitioning between phases at wildly varying temperatures and densities determined by local conditions rather than overall mass. In most diffuse locales far from energy sources like luminous clusters, gas exists as isolated atoms at around 7,000 kelvins, characterized by absorption spectra from elements like hydrogen, calcium, and iron. Denser regions compressed by shock waves or dust grains collect atomic gas at temperatures down to 100 kelvins, dominated by molecular hydrogen, with density hovering near 1 ion per cubic centimeter. In dark nebulae sheltered by dust where stars cannot penetrate, hydrogen gas may further collapse into significant molecular concentrations at tens of kelvins, dense enough that gravity starts weaving filaments comprising as much as 60 trillion ions per cubic centimeter, several billion times higher density than typical atomic cloud envelopes, but still quite tenuous in absolute terms. The diversity of interstellar matter exists across environments, as diverse as comets, protoplanetary disks, and voids separating galaxies. Its variations sculpt ever more complex structures throughout far-flung reaches, while cycling material between stellar ovens and the abyss. Within these fluctuating environments, dust arises as heavy elements ejected from aging or exploded stars condense into solid particles in the frigid darkness. Unlike gas dissipating into transparent atoms and molecules, microscopic dust grains readily radiate infrared signatures, tracing heating up by stellar nurseries, and brightly reflecting visible wavelengths from background stars. Ranging from a few molecules to over a 1,000th of a millimeter in width, dust nucleates ice mantles and grows through coagulation in colder locales. Its presence enables star and planet formation by assisting gas molecules to clump under gravity. Dust also transports organic compounds between star systems and serves as templates for amino acids and other ingredients vital for prebiotic chemistry. While glowing nebulae with their rainbow hues have captured imaginations for centuries, their ethereal forms actually represent but fleeting episodes in the evolution of galaxies and star clusters, sculpted for mere tens of thousands of years by young hot stars before the local interstellar medium disperses. Examples show intricate structures formed through radiation pressure, shock waves, and photodissociation that modify composition and temperature. The famous pillars of creation viewed by Hubble Space Telescope present towering spires of dense molecular hydrogen, 6 light-years in height, illuminated by energetic young stars in the Eagle Nebula. Such transient structures vanish as stellar progenitors burn out, although filaments of dust and molecular gas may persist for longer. Studying the interstellar medium allows astronomers to trace the cyclical nature of matter as it undergoes repeated changes between phases. Within nebulae swirling with new starworth, hydrogen makes up around 70 or 75% of all gas by mass, mostly existing as atomic nuclei, but a significant fraction bound as humble molecular hydrogen. Various isotopes comprise the remaining constituent, including 25% helium along with trace amounts of heavier elements, found predominantly in dust grains condensed in stellar interiors with atoms ejected at death or through stellar winds. The gas cycles through evolutions dependent on mass, whether hot ionized plasma ejecta from supernova heated to millions of degrees or cold dust shrouds shielding molecular formations at 15 kelvins. Scattering of starlight by interstellar electrons and dust enables measurement of density, composition and temperature variations through different signatures imprinted on spectra. Starlight absorbing signature of elements found in dark patches useful for gauging composition. At visible wavelengths, spectral lines from singly ionized calcium and sodium within diffuse clouds indicate transitions absorbing red photons, with ions absorbing ultraviolet radiation from early type stars. Near-infrared spectra show molecular hydrogen dominates at velocity near 3 km per second in clouds where gas condenses without forming new stars. Through microwave and radio telescopes, spectral lines from clouds give composition, density, and dynamics, while polarization maps magnetic fields in cosmic dust grains aligned along magnetic fields, giving view into large-scale organizing forces throughout galaxies. The diversity of the interstellar medium allows habitable zones to arise suitable for planetary systems to emerge. Dense dust cocoons spawn stellar nurseries, while cool, diffuse clouds drift between. Dense nebula spawned the formation in our own solar system 5 billion years ago from enriched cloud of stellar debris that gravitationally condensed into a swirling accretion disk. Dust and molecular clumps condensed planetesimals and protoplanets that grew to terrestrial worlds and gas giants, while the primordial solar nebula dissipated. Throughout galactic evolution, similar processes sculpt habitable environments wherever dust and gas collect sufficient density to collapse gravitationally under their self-gravity or influence of a nearby star and form future planetary systems. The interstellar medium plays a crucial role carving structure within galaxies on largest scales. As massive stars end spectacularly in supernova, shockwaves from stellar explosions propagate at 100 km per second through surrounding clouds, sweeping aside gas and sculpting cavities over dozens of light years across. Such superbubbles blown by stellar associations allow ultraviolet radiation to penetrate over vast regions, ionizing hydrogen within, heating gas to extremes and triggering subsequent generations of starworth atop boundaries, where ionization fronts collide with cooler ambient clouds. On larger scales, rotating spiral arms channel clouds through galactic cores, compressing material enough to gravitationally condense into gigantic molecular rings and bars of star formation witnessed in many spiral galaxies like our own Milky Way. The interstellar medium has recently revealed itself a dynamical structure undergoing flows and movements. Huge magnetic field lines permeate clouds aligning dust grains as tracers revealing vast filaments, and loops thousands of light years in extent, guided by cosmic magnetic fields at unprecedented scales. Vast polarimetric surveys map the structuring influence of magnetism in molecular clouds and identify filaments channeling flows along magnetic flux tubes. The ionized gas also dynamics streaming through in great rivers detectable by their Doppler shifts, tracing vast streaming motions and orbital dynamics of spiral arms at the galactic crossroads. So while the material between stars has traditionally appeared static and uniform, its properties prove to fluctuate wildly contingent on location, with gas sculpted by flows energetic feedback that shape galactic evolution over cosmic epochs. With advancing technology delivering ever more sensitive instruments peering deeper into interstellar realms, prospects arise to discern new intricacies across vast scales. A looming goal involves directly observing molecular signatures from hydrogen fluoride that models predict should exist widely through diffuse galactic plane. Detecting such a ubiquitous molecule would allow precise quantification of total amount of gas throughout Milky Way, with implications for star formation rates. Prospects also emerge to characterize composition and dynamics of galactic halos surrounding disks, where feedback from star formation accelerates gas into low-density regions above and below stellar neighborhoods. By studying diverse environments, astronomers aim to identify how galactic fountains cycle matter between star-forming midplanes and surroundings. Another key hurdle lies imaging evolution of protoplanetary disks, where planets incubate on scales comparable to Jupiter's orbit, yet prove elusive against glare of young stars without coronagraphic techniques. As technology matures, glimpsing such solar nurseries may reveal processes sculpting asymmetries that birth systems like our own, with telltale signatures of terrestrial planets forming through pebble accretion and migration within disks, medleys of dust, ice and gas, spanning a wide range of temperatures and pressures. Similarly, detecting giant exoplanets still amidst formation within embryonic disks may offer unprecedented views into planetary construction in action, illuminating how architectures like our own solar family arise from swirling protoplanetary birth environment. Each advance pushes comprehension of interstellar matter, mediating cosmic processes to new frontiers. In conclusion, the interstellar medium should no longer be viewed as mere transparent void, but rather an intricate, dynamic entity vital to galactic evolution across epochs. Its varied phases between stars sculpt environments where new suns ignite within dense clouds, and habitable planetary realms coalesce from leftovers of stellar alchemy. A key question contemplated by astronomers involves appropriate environments within galaxies capable of supporting life. Certain preferred locales must offer favorable conditions for worlds hospitable enough that biological processes can emerge and evolve over eons. While star systems like our solar neighborhood specifically mediate Earth's circumstances, overarching galactic setting also impacts habitability over multi-billion-year timescales. Zones exist throughout spirals, where planetary environments remain conducive to genesis and complexity of organisms. This concept delineates regions termed the galactic habitable zone, delineating preferred habitable territory for emerging and persisting life. Life likely demands mild stellar neighborhoods avoiding extremes. Fluctuating heavy element abundance throughout galaxy evolution grants more prospects earlier when heavier building blocks like carbon-saturated interstellar medium following first star generations. Life also favors stability, minimizing catastrophic influence. Older sections prevailed billions of years, permitting intricate organisms. Thus, galactic habitable zone likely situated a Goldilocks distance from galactic core, avoiding hyperactive volatility, while metal enriched for complexity. Our solar system, positioned ideally approximately 25,000 light-years outside dynamic core, amongst numerous solar-type stars, furnished stable neighborhood over billion-year history. A galactic habitable zone arises from balance between opposed factors, impacting habitability on multi-million-year timescales. Besides stability, developing complex life requires common heavy elements synthesized through previous stars. Greater density near core supplies heavier elements, but risks disruptions, while outskirts lack essential enriched building blocks. Other factors like radiation from cosmic rays also impact habitability along galactic radius. Denser cores expose young planets to X-rays ionizing primordial atmospheres, blocking prebiotic chemistry. Regions between inner and external galactic radii prove optimal zones for complex life if enjoying adequate metallicity and calm stellar associations. Location amidst tightly packed stars favors risks on galactic neighborhood disruptions, negating necessary stability across eons. Our Sun's distance approximately halfway between core and halo presumably proves ideal seclusion from crowded cores, yet furnished by older generations. Near galactic anticenter anti-rotation direction 8,000 light-years, farther lies another habitable scenario, benefiting from reduced stellar encounters with spread associations. Their complex life faced lower extinction risks, if emerging, benefiting longevity. Other regions provide suitable locales if enriched in heavy elements, allowing complexity over periods required for advanced organisms. Beyond prime galactic habitable zone, outer fringes face scarcity of heavier elements along with galactocentric radiation hazards and reduced probability interactions enabling panspermia transfer life between planetary systems. More distant reaches lack enriching stellar debris nurturing complexity. However, within halo outskirts could arise regions holding planets in conditions mild enough for simple biospheres to subsist over billions of years if supplied sufficient essential elements from previous stellar populations settling nearby at early epochs. Understanding preferred locales permits refining search for habitable exoplanets within our Milky Way and other galaxies, hinting where life could survive and emerge. Other factors further refine galactic habitable zones on million-year timescales key to habitability. Stellar density impacts formation of planets with sufficient masses and chemical abundance necessary for life, as we know it, since inhabiting planets smaller than Earth face challenges retaining enough atmosphere preventing water from evaporating. Stellar neighborhoods with higher densities spawn more gas giant planets through disk fragmentation, however increase risks collisions, stripping away atmospheres. Regions between spiral arms with 500,000 stars per cubic parsec prove too sparse, limiting diversity of planetary system architectures where life favorably arises. Migration of planetary systems between galactic radii over billions of years through galactic orbits also impacts habitability. Close flybys among stars disrupt developing planets, stripping away atmospheres, or imparting velocity kicks scattering planets from habitable zones. Habitability must accommodate for changes in heavy element abundances as systems traverse diverse galactic environs over lifetimes. Planets emerging in optimal enriched regions could migrate outward facing metallicity depletion preventing complexity, then migrate inwards facing hyperactive instability. Stable zones minimize disruptive migrations, enabling steady habitable environs conducive to biological evolution over requisite multi-billion-year timeframes. Orbital parameters around parent star critically impact climate history on terrestrial planets, bearing directly on potential for life. High eccentricity or obliquity induces climatic extremes, preventing complex life from establishing, while circumstellar habitable zone boundaries shift due to changing luminosity along parent star's lifetime, necessitating planets maintain stable orbits. Planetary dynamics must avoid irregularities amplifying temperature swings, disrupting biospheres over geological eras. Galaxies contain carefully situated regions with attributes aligned for developing suitably temperate and enduring habitable environments on multi-generation timescales. Composition differentiates amongst galaxies impacting preferred locations. Younger, metal-poor elliptical and irregular galaxies demonstrate less widespread enrichment, reducing habitable zone sizes. Greater proportion population EU and population I-stars lack heavy elements, building biochemical complexity essential for advanced organisms. Meanwhile, larger barred spiral galaxies like Milky Way possess more population I-stars, granting wider habitable ranges. If planetary system formation reflects birth environment, barred spirals birth more potentially life-supporting systems, since these structures channel molecular clouds funneling into prolific bursts, seeding stellar generations. Over cosmic time, galactic habitable zones migrate along with stellar populations. older galaxy generations exhibit smaller habitable extents further from cores following early metal-deficient enrichments. With time, enriching stellar generations widen heavy element abundances, pushing habitable zones radially inwards where building blocks accumulate. For Milky Way thick disk, older populations born beyond current boundaries in less enriched circumstances, later enrichments migrate habitable zones inside over tens of billions of years. Migration of habitability conditions arises as galaxies chemically evolve, allowing life throughout galactic histories across spatial and temporal epochs as enrichments expand conduciveness to complexity. Certain external and dwarf galaxies pose intriguing possibilities as reservoirs for simple life. While lacking capacity to evolve advanced organisms requiring rarest elements, these low metallicity systems keep stable enough environments over mega-annum timescales viable for microbial subsistence. Microbial mats surviving marginal conditions representing basic life primary evolutionary stage should not preclude such galaxy members. External galaxies like Canis Major Dwarf Spheroidal Galaxy offer sites sheltering ancient microbial ecosystems, occupying stable physical niches since early epochs, persisting in isolation, lacking interactions, spurring complexity. Simple life may inhabit the ancient fringes of galactic habitable zones, wherever minimal conditions persisted over aeons. Galaxy interactions impacting distribution of interstellar matter also influence zones conducive to long-term habitability. Gravitational torques from galaxies circulating within cluster environments distort gas flows, stimulating instabilities. Major galaxy mergers disrupt galactic structures, however, also stir enrichments, mixing chemical abundances to broader ranges, seeding later generations, including epochs amenable to complexity. Remnant disks left following such disruptive episodes could seed rebirth of galactic habitable zones as newly enriched gas accumulates into revived spiral patterns. Even destructive episodes may revive preferred conditions on multi-billion-year timescales when integrated across entire clusters over Hubble times. Technological civilization emergence demands specific prerequisites absent during our era's early solar system assembly. Increasing metallicity over cosmic time impacts required conditions to support advanced intelligent organisms capable manipulating environments and harnessing energies permitting spaceflight. While limited environments suffice lower life, civilization demands enrichments supplied through later stellar generations across billions of years. Our Milky Way suburbs include optimal metallicity ranges approximately 10 times primordial abundances supportive of civilization emergence across multi-billion-year windows. Likewise, other galaxies contain epochs and territory enriched to tolerances, allowing advancing civilization birth should life survive disruptions as galaxies chemically progress. While galactic habitable zone constitutes preferred solar neighborhood contexts, myriad other factors also shape planet climate histories, bearing directly on biosignatures our instruments may someday detect. From stellar influences regulating temperatures across geological timescales to individual planet properties impacting atmospheric evolution through dynamical settings molding seasonal variations, habitability depends intricately on system architectures. Mapping galactic territory, enabling complexity over prolonged epochs, affords framework to guide targeted searches for signatures beyond our solar system. By considering environmental influences throughout galaxy, astronomers refine expectations, discovering signs of life taking root across cosmic arenas. With future instruments mapping nearby galaxies in finer chemical detail, astronomers may identify diverse galactic habitats throughout cosmic evolution, accommodating microbial subsistence over billions of years as enrichments distribute. Through refined galactic models and panchromatic surveys mapping stellar populations, astronomers narrow windows of galactic environment potentially conducive to complexity on par with favorable epochs within Milky Way. Surveys combining observational constraints with theoretical explorations may yield greater insights into cosmos reservoirs capable of breeding not just simple life, but advanced features like intelligence given sufficient time. Mapping habitability through galactic time seeks common biochemical niches across the universe. Since earliest records, humans observed lights moving slowly amongst more rapidly shifting stars, speculating these as other inhabited worlds. Though modern astronomy confirms these slow congregations comprise planets encircling nearby stars, questions remain whether signs of life exist beyond Earth. Potentially habitable exoplanets inspire imagining living systems evolving independent of humanity's experience. While direct imaging capabilities remain limited, sensitive instruments detect atmospheric fingerprints, hinting at extraordinary biospheres. Growing understanding of conditions supporting complex chemical networks suggests potential for living diversity matches variety across stellar landscapes. However, confirming extraterrestrial biosignatures requires attaining unprecedented observational clarity into environments differing from prototypes. While technology continues improving to unveil exoplanetary architectures amenable to habitability, current limitations preclude capturing distant images. However, transit photometry quantifies atmospheres during silhouettes cast before host stars, dimming light in distinctive wavelengths betraying elemental skies. Spectroscopy deciphers stellar spectra filtered through planetary atmospheres, imprinting signatures influenced by biology. Exoplanetary science seeks signs like saturated biosignature gases exceeding expectations from abiotic planetary conditions, or co-evolving disequilibrium mixtures stabilizing favorable temperatures. Oxygen particularly interests astronomers since arising physiologically on Earth, albeit abiogenetic sources complicate interpretations absent context elsewhere. Additional clues involve methane signatures diverging from expected geological fluxes. Curiosity inspires modeling diverse abiotic and living worlds. Terrestrial exoplanets likely exhibit variability exceeding solar system prototypes. Some potentially consist entirely ocean-covered with continental surfaces submerged like hypothesized ocean planets. Others hypothetically comprise silicate-dominant compositions unlike rocky, metallic, icy or atmospheric worlds familiar here. Gas giants beyond Neptune-sized thrive populating galactic neighborhoods. Hypothetical high-sin planets amalgamate characteristics like many Neptunes, including vast oceans underlying hyperdense atmospheres maintaining liquid states, where pressures prevent vaporization under intensity exceeding Jupiter. Their hypothesized plentifulness hints opportunities for unique forms of life if chemistry permits. Biosignatures require differentiating living signatures from abiotic mimics. Possible biochemical stowaways transported via meteorites seeding prebiotic materials complicate interpretations without contextual data. Habitability depends intricately on irradiance levels, stellar spectra, atmospheric pressure, composition, climate forcing, plate tectonics, oceanic circulation, and nutrient cycles supporting complexity. Biospheres probably vary chemically compared to Earth under dissimilar environmental filters. Perhaps alternative biochemistries evolved adapting to regimes like icy or gas/liquid interfaces. Characterizing exoplanet architectures and atmospheric compositions proves prerequisite to identifying divergent signs of life adapted independent of humanity's template. Further insights derive from solar system comparative planetology. Terrestrial prototypes offer tangible habitability parameters against which contextualize emerging exoplanetary discoveries. Mars furnishes lessons regarding signatures retaining hints of ancient life under changing climates, despite present atmospheric thinness. Enceladus and Europa intimate potential subsurface worlds, sustaining exotic organic-based ecosystems insulated from surface extremities within liquid water oceans contact with rocky interiors. Titan's hazy methane shroud suggests non-oxygen reliant metabolisms may thrive via alternative chemistries. Gas giant moons like Ganymede demonstrate opportunities even low atmosphere/vacuum terrestrial surfaces if energy flows sustain chemistry. Comparative studies enhance recognizing divergent signs of life on unfamiliar worlds. Naturally, identifying and interpreting signatures remains challenging without contextual data. Comparing planetary orbits, masses, radiative balances considering stellar types/evolutionary stages better reveals candidates naturally selecting temperate parameters. Archean Earth analogs see most perspective, however less forgiving M-dwarf systems prove common, necessitating adaptation. Measuring atmospheric ratios against changing stable isotope ratios throughout stellar lifetimes helps disentangling abiotic/biological effects. Characterizing host stars provides foundation interpreting environments and energy flows shaping emerging biospheres. Multi-wavelength observations surveying molecular composition assists recognizing potential disequilibrium mixtures diverging from physico-chemical baselines. With sufficient contexts, spectral signatures could reveal extraordinary life. While technology continues improving observational capacities, current spacecraft limitations preclude close characterizations of most promising candidates. However, upcoming facilities may revolutionize biosignature detection prospects. The James Webb Space Telescope launching next year aims detecting atmospheres of super-Earths transiting M-dwarfs, characterizing volatile inventories and mineralogies, hinting habitability. Its unprecedented spectroscopic surveys efficiently characterize candidates through transit/emission photometry. Europe's Ariel observes cooler stars ripe for temperate terrestrial system assembly, comprehensively characterizing exoplanet atmospheric compositions towards discerning biosignatures. NASA's Habitable Exoplanet flagship concept builds upon such efforts with integral field spectrographs, resolving spectral features over extended wavelength ranges. Future missions marrying flagship-scale observatories with constellations carrying out comprehensive surveys offer unprecedented biosignature detection prospects. A mission consortium like LUVOIR pair large segmented space telescopes for high-resolution exoplanet spectroscopy with smaller scopes performing statistical population studies. Others envision formation-flying telescope arrays comprising coordinated small/medium telescopes enabling high-resolution coronagraphic imaging. Combining small telescope fleets, optimized photometry, and high-resolution spectroscopy maximizes discoveries. Multi-spacecraft coordinated efforts achieve order-of-magnitude leaps, resolving exoplanet atmospheric compositions across populations toward finding signs of habitability and life. Naturally, the most promising biosignature detections arise through studying temperate terrestrial exoplanets like super-Earths with significant atmospheres and liquid surface water, yet few candidates near enough appear amenable to comprehensive characterization. Future large direct imaging missions hold potential identifying habitable Goldilocks zone terrestrial worlds, targeting temperate super-Earths around nearby M-dwarfs, frequently transiting observable for extended periods. Nearby candidates like Proxima Centauri offer tantalizing possibilities if confirmed inhabitable and characterized spectrally toward biosignatures with next-generation telescopes. However, current non-detections around near K dwarfs suggest temperate terrestrial systems may remain elusive until even larger space infrastructure emerges. Whether detecting biosignature gases constituting independent evidence extraterrestrial life exists or gaining sufficient contextual data constraining atmospheric origins, while revealing extraordinary architecture potentials, future instruments promise unveiling habitability and life across worlds differing from Earth. Though technological barriers remain significant, incremental advances continue narrowing constraints, defining where and how life adapts to diverse ecologies. Studying temperate planets represents only the first step toward comprehensively characterizing biospheres outside Earth's paradigms. As astronomy matures, resolving myriad environmental influences across galactic sightlines, Observers edge nearer, illuminating life's full diversity populating the spaces between stars. For centuries, astronomers noted centers of galaxies harboring concentrated luminous sources outshining entire systems. Gradually, insights accumulated realizing such phenomena represent supermassive objects at galactic cores accreting prodigious material. As theoretical predictions emerged, describing gravitationally collapsed states producing immense densities, mounting evidence supported enigmatic centers comprising black holes billions times more massive than suns. Today, instruments across spectrum capture dynamics within event horizons, shedding light on monumental singularities, place sculpting cosmic vastness over aeons through colossal ingurgitations dominating galactic nuclei. Black holes form through catastrophic gravitational collapses, following stellar deaths when cores exceeding 3 solar masses implode past neutron star configurations. Large collections centralized near galaxies' dynamical centers likely arise through mergers accumulating initial masses seeding runaway growths. As dense cores form dynamically through collisions or interactions accumulating primordial gas clouds, main sequence stars plunge inward, fueling escalating engorged masses millions times stellar through gravity's unforgiving consequences. While exact growth mechanisms remain theoretic, accumulations now approach billions solar masses regulating galaxy evolutions. Gravitational attractions prove irresistible concentrating material amid violent collisions concentrating mass under region's own self-gravity within vast collisional dark matter halos permeating early galaxies. Growing masses gravitationally capture vagrant stars, accelerating accretion rates dramatically. Accumulations seeded with merely stellar protocores swelled epochally through self-augmenting feedings, becoming disconnected from births, yet steering galactic evolutions across billions years. Observable consequences involve immense attraction spheres dominating stellar motions amid churning plasma swirling ever inward. While exact seeding history is uncertain, runaway growths clearly establish centers amid luminous activity sculpting spiral arms. Size correlates tightly with host galaxy qualities indicating coevolution. More massive galaxies harbor larger central singularities according to broad empirical relationship. Specifically, supermassive black hole mass represents approximately 0.1 to 0.2% galaxy's total stellar bulk. Connections imply symbiotic growths governed self-regulating feedbacks between dark kernels and galactic populations across vast realms. How singularities formed at centers from initially stellar protocores remains hypothetical, yet growths clearly establish intimately linked to forming galaxy distributions through intricate self-limiting mechanisms. Detectable across vast sightlines, correlations embody landmarks elucidating galaxy black hole codependence since early universe. Twin observational pillars detect supermassive black holes through luminous consequences reprocessing in falling matter. Firstly, intense spectral lines emanate from accretion disks, condensing into spiraling structures amid gravitational attractions. Material collisionally heats, generating intense visible ultraviolet luminosity outshining entire galaxies once concentrated sufficiently. Secondly, enormous relativistic jets propel opposite polar directions whenever actual rotation present. Matter achieves near-luminous velocities before being channeled along magnetic field lines, spewing light across megaparsecs. Prominently detected across radio, processes trace supermassive particle accelerations regulated through forces governing dynamics within event horizons. Accretion powers spectacular emissions surpassing normal stellar processes. Deep potential wells compress and heat diffuse gas into configurations matching theoretical profiles. Innermost zones superheat, generating thermal continuum radiation, peaking within visual regimes. Outer regions generate narrow emission lines recombining under intense conditions. Doppler shifting maps spinning and reveals emission structure. Material circularizes, forming flattened arrangements aligned perpendicular spin axes where collisions propel heating. Temperature varies across radius while density drops precipitously inward. Spectra probe physical conditions through radial distance, betraying Enigma's hidden depths, fueling spectacular luminosities concentrated across billions solar masses. Active galactic nuclei ejecting relativistic beams detected across vast radial lobes provide clearest marker tracing back to central engines. Beams originate within core parsecs, accelerated along field lines aligned spin axes. Driving mechanism involves rotating black holes dragging inertial frames, converting rotational energy into directed particle acceleration once orientated significantly off-axis. Resulting synchrotron emission traces outward shocks throughout lows, often exceeding million light-years. Such jetted activity betrays spin-powered processes within event horizons themselves, accelerating material to 99% light speed. While inner workings remain occulted, outputs trace intimate connections between singularities and furious activities, sculpting galactic evolutions across epochs. Lingering questions involve spinning black holes' role generating jets, where rotation orientation established. Theoretical models relate spin paradigm to accretion flows feeding central engines. Prograde infall aligning net angular momentum along rotation axis spin black holes up efficiently, establishing powerful jets oriented polar directions. Conversely, retrograde accretion counters rotational direction, possibly suppressing jet formations altogether through field perturbations. Such scenarios remain hypothetical. However, spin paradigm describes connection between infall direction and resulting jet power observable across billions years. Precisely aligning rotation through magnetic fields powered jets links directly to spin-powered mechanism, accelerating material relativistically. While central engines strongly influence large-scale structure through feedbacks injecting prodigious energies, singularities themselves remain fundamentally mysterious. Despite theoretical predictions and unambiguous empirical correlations, event horizons mask all gravitoelectromagnetism near Planck scale. Yet gravitational pull warps light itself, revealing silhouettes betraying spacetime curvatures near limits comprehension. Through measurement, anomalous stellar orbits mapping gravitational potentials, singularities' existence becomes observationally indisputable, whether directly viewable or complete occulted. Future breakthroughs may glimpse boundaries separating fathomable physics from enigma through observing extreme phenomena akin quasars blurring light. Yet mysteries remain whether horizons fundamentally black, while feedbacks clearly sculpt galactic majesty overall. While central engines eject jets dramatically shaping large-scale morphologies, feedback also operates more subtly, sculpting galactic nuclei through winds emerging accretion disks. Continuous ejection blowing bubbles throughout contains instabilities regulating further accretion, thereby self-limiting growths, establishing relationship between bulge and black hole mass. Precisely how winds couple between innermost regions and galactic scale bulges governs tight correlations across masses. Winds expel matter via photon pressure heating and scattering energetic particles, evacuating deep potentials established through successive merger histories. Feedback forms galactic metabolic cycles, sustaining coevolution through balanced growth. Exploring mysteries surrounding connections between galaxies and central singularities, illuminating both cosmic large-scale structure formation, remain open questions across disciplines. Through multi-wavelength surveys, coordinating observatories, pushing instrumentation capabilities, meanwhile theoretical models incorporate insights continuously accumulating, enigmas surrounding earliest black hole seeds, and self-regulating growths governing ongoing galaxy-scale feedback loops comes increasingly clear. Origins related intrinsically to first structures continue clarifying across sightlines into infant universe. Yet event horizons by nature occult inner realms where physics diverges from comprehension. Through statistical analyses synthesizing information across diverse sightlines mapping connections over cosmic epochs, mysteries surrounding remarkable cores remain illuminated further, so role galactic regions play shaping visible universe becomes ever clearer. While singularity boundaries occlude deeper insights, consequential outputs across spectrum present windows into structures calibrating hierarchical formation theories through cosmological epochs. Precise measurements correlating black hole masses against host galaxy properties fundamentally underlies cosmic structure growth across scale. As instrumentation capabilities progress toward resolving galactic nuclei dynamics across growth histories, our comprehension of linked convolution cycles maturing galaxies and centrals reaches new depths. Through massive surveys uniting gravitation theory with observable properties across populations, convolution paradigm serving as cornerstone for LCDM cosmological model receives ever tighter empirical validation. Revolutions like future flagship missions may even capture extreme phenomena like jet seeding nearing event horizons, elucidating fundamental mysteries surrounding relativistic outcomes of unparalleled gravitational concentrations. Although gravitational regimes enclosing singularities exceed direct glimpse, feedback expressions clearly sculpt galactic architectures across light years, connecting galaxy bulges with central nuclei over billion-year sequences. Fierce winds propagate instabilities regulating ongoing stellar, gas, and black hole growth through time. In turn, regulated feedback molds future cycles, fueling star birth from recycled material. Interplay represents galactic metabolism, sustaining stellar component within darkened hearts across cosmic epochs. While depths still occlude empirical signatures across electromagnetic spectrum, prove supermassive bulwarks definitively exist, impacting visible structure formation, while directly connecting galaxy and black hole coevolution over cosmic history. Our view beyond Earth offers brief window into vast cosmos, populated by countless galaxies far beyond comprehension. Yet, even nearby satellites easily spotted adorning night skies afford close perspectives impossible elsewhere. Brighter companions long known circling outskirts like Magellanic Clouds number among closest galactic neighbors, visible panoramas furnished by proximity. Residing barely 1/6 Andromeda's remove, these dwarf irregular systems enlighten our understanding galactic interactions and faint building blocks populating stellar environments over epochs. Their youth and isolation render pristine relics, preserving signatures critical to decoding cosmic structure formation, impossible gleaned anywhere more distant. Historically, earliest observers identified Magellanic Clouds as nebulae separate from Milky Way by virtue position amongst background stars. However, only modern astrophysics establishes nature dwarf galaxies orbiting between 160,000 and 210,000 light-years distant, closer than any galaxy past Andromeda. Their orbital properties follow paths elongated perpendicular disks while carried around Milky Way center once each billion years. Close proximity allows dissecting internal stellar populations with unprecedented detail through telescopes, whereas more remote systems remain point sources. Their galactic membership grants unique settings, examining satellite-host interactions, sculpting morphologies over eons. Of two principal components, Large Magellanic Cloud measures 14,000 light-years wide, containing 30 billion stars, dwarfing Small Magellanic Cloud, half-width, containing 3 billion members. Despite modest scales versus Milky Way's 200 billion stellar population, diversities arise within Magellanic galaxies furnishing detail comparable major local group galaxies. Stellar complexes, OB associations, variable stars enjoy designation matched Andromeda or Triangulum with clarity impossible for more distant objects. Ages, metallicities, spatial chemistries betray distinct generational signatures, enabling tracing galactic nurturing against more obscured influences encountered. Magellanic Clouds likely began independent dwarf galaxies, subject gravitational influence Milky Way across aeons. Through repetitive close passages experiencing tidal forces, morphologies distorted spawning creation bridges, stellar material connecting systems. Particularly spectacular bridge 3/4 light-year, wide arcs 90,000 light-years, linking large cloud to Milky Way's halo. A second stream connects both systems, likewise populated countless stars, shed from gravitational interactions between larger companions across multiple close passages. Affects scoped system interactions clearly unlike encounters between fully collisionless dark matter halos alone. Milky Way tidal stress molded complex structures within clouds over timescales. In large cloud, bar formation concentrates stars along extended central distributions. Meanwhile, in small cloud stellar populations, symmetrically distributed unlike lopsided large neighbor. Their elongated shapes signify past deformations, disrupting initial axisymmetric morphologies as tides ripped material toward Milky Way, while systems drew near pericenters. Motions trace orbital patterns clearly subject to tidal influences, unlike more isolated dwarfs evolving via internal instabilities alone. Their elongated configuration's parallel orbit path contrasts more circular Andromeda and Triangulum, preserving initial isolation. Unlike other major local group galaxies where intricate spiral patterns predominate, Magellanic systems favor irregular structures, due dominance low mass, and resultant feedback processes dominating internal evolution. Specifically, supernova disperse enriching heavy elements across clouds, preventing further efficient star formation through pressure regulation. Still isolated regions concentrate massive stars birthed from molecular complexes compressing through self-gravity. Spectacular 30 Doradus, nebula within large cloud, constitutes among largest star-forming regions within local group, visible unaided eye from southern hemisphere. Towering pillars rising several light years, sculpted via radiation pressure from energetic stars, remain unprecedented in detail. Chemical tagging establishes enrichment patterns through galactic epochs. Early stellar generations dominated by population IOV stars left incomplete mixing nucleosynthesis products. Later populations EU and I steadily elevated metallicities concentrating elements from successive supernova. Abundance dichotomies between field stars against populations within centrally concentrated zones trace spread across clouds. Metal poor, -1.5 F/Hg. Ancient fields compared, -0.7 F/Hg. Centrals identify initial mixing preceded irregularly contra-spiral distributions. Absences young population I metal-rich stars further identify quenched recent evolution, since close Milky Way approaches stripping star-forming gas. Comparisons against more luminous spirals further reveal stellar feedback dominating evolution across clouds, unlike more efficient circulation throughout larger potentials. While certain systems contain extensive reservoirs, molecular hydrogen, fueling further star formation episodes, close passages Milky Way across billions years stripped substantial reserves, binding material necessary gravitationally collapse. Affects mimic interactions observed ram pressure stripping dwarf irregular satellites within more massive halos, depriving future generations. Their small masses fail gravitationally bind constituents, exposed Milky Way's million-degree corona between passes. Peaking above/below disks also favors material removal versus more protected dorsal encounters shielded by extended gaseous layers. However, reservoirs persist, indicating ongoing starbirth when undisturbed despite environmental influences, gradually shutting down efficient formation over coming epochs. Magellanic clouds persist little altered state for close galactic satellites. Their ongoing evolution shaped across billions years future interactions, Milky Way itself remains unpredictable. whether systems survive next 3 periapses intact or faces complete disruption into tidal tails, connecting with stellar halo over forthcoming gigayears remains open question. Some models predict large cloud disrupted latest passage, whereas small cloud follows independent evolution over longer period less elongated orbit. Others forecast both endure next few orbits, dynamically unchanged. Their complex morphologies, enrichment patterns through time, and projected fates offer critical templates decoding satellite-host interactions across epochs, underscoring role environmental processes, play-shaping galactic building blocks throughout cosmic history. While Magellanic clouds represent only minor satellites within local group, examples illustrate diversity evolutionary paths even small galaxies experience, subject external forces. As with all cosmological objects, Roll's environmental factors exert influence intrinsic properties through tidal encounters, gas stripping or merging, dictate fates across epochs. Their past and ongoing transformations furnish paradigms for interactions sculpting galaxy morphologies between scales. Modern observations dissecting their stellar populations, kinematics, gas reservoirs, and enrichment histories thereby extract critical cosmological context otherwise impossible glean. As Milky Way's nearest galactic neighbors, Magellanic clouds forever enlighten galactologists regarding interactive roles between galaxies shaking structures across visible universe. Across unfathomable expanses intervening galaxies, islands emerge populating cosmos at enormous scales, orders magnitude beyond solitary systems. These spectacular galaxy clusters aggregate thousands individual units throughout common dark matter halos, deep gravitational potential wells containing trillions solar masses collectively. While individual galaxies remain point sources even nearest, concentrations number among largest coherent structures coherent across sky. Within, diverse populations interact dynamically across epochs, sculpting intricate structures, tracing formation over billions years since ancient universe through multiple generations stars. Their enormous scales grant unmatched opportunities to study cosmology's crowning objects across eras. Gravitational attractions first concentrate dark matter across scales 100 million light-years, then galaxy seeds assemble following filaments, stringing between concentrations inspiring web's intricate structure across sightlines. Though occupying mere percentage observable universe volume, according density contrasts highest realms known influence gravitational lensing across eons. Potentials wells within cluster environments sufficiently massive retaining even X-ray emitting gas million Kelvin temperatures across lifetimes Hubble time through virial heating infall, enabling direct probing into deep potential basins unlike cooler individual galaxies. Among most populous galactic configurations, Coma cluster spans over 3 degrees arc across sky, containing thousands individual galaxies, trillions solar masses, total within hundreds millions light-years diameter halo. Visible unaided eye from northern hemisphere, Coma presents awe-inspiring panorama enormity across sightlines. Though individual point sources remain too dim distinguishing morphology close inspection, full complex reveals spectacular arrangement tracing underlying dynamics, dominating evolution epochs since early cosmic dawn. Surveys reveal intricate galaxy morphologies dwarf ellipticals, unlike isolated spirals, tracing formation histories across vast stellar populations. Despite enormous scales, only gravitational interactions dynamically coupled galaxies throughout common potential, rather merging unlike individual collisions. Rather effects subtly shape evolutions across eras through rare close passages exerting tidal forces, gently perturbing outer disks, sparing central bulges, yet transforming morphologies irregularly. Tidal stripping removes outer material across intervals between pericenters over gigayears, while affecting stellar populations, gently across generations. Ram pressure stripping meanwhile disperses diffuse gas encountering intracluster medium million Kelvin temperatures, restricting future star formation. Influences cooperate, sculpting galaxies, morphological diversity, resembling spirals yet shaped subtly unlike isolated evolution. Intracluster mediums constitute another fascinating galactic constituent, emerging early universe heating trace expansion cooling across eons. Comprising primarily hot ionized plasma million Kelvin temperatures across hundreds millions light years, arising shock heating ongoing structure formation across epochs, mediums envelop entire clusters luminous X-rays across sky. Although rarefied densities merely 100th cubic centimeter, sheer cluster scales concentrate mass rivals contained galaxies collectively, while dominating dynamics across trillions years. Formed through gravitational compression in falling material during hierarchical assembly, meanwhile heated shocks between colliding, ongoing accretion maintains temperatures cooling through atomic processes. Radiative losses balanced further accretion maintain steady state across periods compared Hubble time. Luminous X-ray glow betrays titanic scales mediums while permitting glimpse into clusters potential wells otherwise inaccessible. As hot plasma resides hydrostatic equilibrium under common potential, emission distribution traces overall matter distribution. Spectroscopy deciphers plasma physical conditions, including temperature profile across radius illuminating processes governing evolution since formation. Spectacular instruments today capture concentration's finest detail, spanning over degree across sky far surpassing extent individual galaxies. Multi-wavelength mappings further reveal concentration's intricate internal structures across spectrum, enriching cosmology understanding structure growth since inflationary epochs. Specifically, powerful telescopes map plasma resolving sub-kiloparsec structures, finest known baryonic filaments across extended universe. Gas dynamics further betrays environmental influences, subtly shaping galaxies across vast scales, unlike isolated rotations within individual disks. Ram pressure stripping systematically removes diffuse gas reservoirs, disrupting future star formation episodes, especially impact late-type disk galaxies entering cluster environments after forming outside, then transformed early types through gas removal. Meanwhile, interactions turbulences excite gas, triggering localized episodes starworth before removal. Stripping indirectly redens galaxy colors, quenching star formation through multiple mechanisms across durations compared Hubble time. Consequences emerge through comparative studies systems within versus beyond clusters, tracing environmental processing across epochs. Perhaps most spectacular phenomena involves particle accelerations generating clusters extended radio lobes over megaparsec scales. As galaxies orbit within mediums, shockwaves form boundaries, compressing gases funneled along large-scale filaments, sculpting cosmic web across era. Shock accelerations inject relativistic electrons into surrounding plasmas through Fermi mechanism, generating synchrotron emission across radio through interactions ambient magnetic fields. Resulting luminous emissions produce spectacular bridges arsing beyond individual galaxies, tracing pathways in falling surrounding within clusters' cores. Largest emit over 100 kiloparsec, far surpassing extent galaxies, sculpting environments across trillions years. While radiative losses remains insignificant against heating through structure formation, feedback also self-regulates intracluster medium through central active galactic nuclei jet eruptions, injecting vast energies throughout environments. Specifically, central supermassive black holes accrete, powering extended bipolar jets propelling light across megaparsecs upon galaxies' collisions within high-density cores. Fan beams heat surrounding plasma, significantly suppressing future accretion, consequently cooling across areas. Phenomena remains active throughout massive clusters, balancing radiative losses, maintaining quasi-equilibrium across Hubble timescales. Interplay between heating accretion, cooling establishes steady through self-regulation across scales. relationships emerge connecting intracluster mediums properties, specifically temperatures against cluster masses, through refined scaling observations across multi-wavelength surveys. Slopes depict expected scale in virialized structures, assuming self-similar collapse where scale sizes, densities proportional mass. Slight deviations potentially attributed non-thermal pressure support, involving feedback processes magnetic fields influencing scaling. Distributions further establish clusters among largest virialized objects throughout cosmos, tracing gravitational assembly since structure commencement. As largest concentrations baryonic ordinary matter across scales approached Hubble lengths, evolution connectivity between plasma galaxies, fundamental cosmological questions surrounding structure growth across epochs. While individual galaxies prove exceedingly difficult untangled collisions mergers cluster environments, scaling laws connect properties luminous intracluster plasma masses, permitting glimpse into gravitational potentials across largest scales feasible presently. In tandem statistical tools applied distribution morphologies, stellar populations across members further divulge environmental impacts across epochs, since these concentrations emerge scales 100 million light-years. Understanding interplay between galaxies' gravitationally sculpting divers morphologies through rare tidal interactions ram pressure stripping directly probes cosmological assembly hierarchical structures traced largest scales today. Multi-wavelength observations across spectrum combine extract invaluable context surrounding formation concentrated scales shaping into future. For millennia, humanity gazed skies wondering nature cosmos. Only modern astrophysics unlocked mysteries through meticulous observations aided daring theories. Chief revelation entails cosmos' dynamic entity constantly waxing. Galaxies throughout observable universe redshift light proportional distances, cosmological expansion tiers, fabric spacetime itself driving apart across eons. Journey comprehending background fabric, conducted through patience precision gathering evidence across frontiers knowledge. Piece by painstaking piece, picture coalesced stunning reality continual inflation galaxies racing apart against horizon forever receding since primordial fireball. Initial stepping stones involved Vera Rubin, detecting spiral galaxies, rotational velocities exceeding theoretically predicted decline outward according Newtonian expectations. Measurements in plane unseen masses permeating disks circularizing outskirts. Coinciding evidence emerged from astronomer Hubble mapping relations between galaxies observed redshifts proportional distances. Redshift frequency light lengthening wave crests, shifting visual spectrum infrared proportionate velocities preceding sources. Findings harmonized predictions general relativity expansion stretching photons en route observers according metric expansion. Theoretical framework arose cosmological principle postulating homogeneity isotropy throughout cosmos. Detailed analyses redshift distance correlations refined through precision instruments calibrating cosmic distance ladder encompassing stars' Cepheid variables, establishing relationships between intrinsic brightnesses, periods pulsating variable class Cepheids furnishing standard candles. Supernova type Baia further exploited, proving exceptionally consistent luminosities, furnishing additional rungs ladder extending comprehension, cosmos geometry topology across eons. Introducing concept standard candles, enabled measurements exceeding local group reaching zillion light-years, deducing expansion rate Hubble constant approximating 70 km per second per metaparsec. Together evidence implied universe dynamic state flux inflating like loaf bread dough. Curvature spacetime fabric itself, accelerating apart galaxies beyond Newtonian expectations gravity alone. Further insights emerged theoretical work, postulating early universe underwent inflationary epoch hyperexpansion exponentially faster light, split-second generating homogeneity isotropy across horizons. During inflation hypothesized short-lived exotic form energy dominated mass energy drove unspeakably rapid growth. Astronomers scan today originated infinitesimal point, scarcely larger subatomic particle. Inflation seeded quantum fluctuations, density perturbations manifesting galaxies clusters across sky, while stretching spacetime flush. Within seconds inflated many times size observable universe today, endowed pristine uniformity, enabling formation cosmic web structure observed. Inflation hypotheses received strong confirmations. Precision measurements microwave backgrounds by WMAP Planck observatories captured imprints quantum noise fluctuations during inflation match theoretical predictions near perfectly. Accumulating observational anchors calibrated expansion rate crucial cosmological parameter, today known approximately 70 kilometers per second per metaparsec, corresponding age 13.7 billion years, since Big created everything observable from nothing. Calibration also established density parameter describing mixed matter versus gravitational attraction throughout observable cosmos, barely sufficient halt ultimate expansion given time. Specifically, portion density exceeding critical threshold required decelerate, measured around 0.3, implying dark energy dominates mass energy necessary curvature recollapse, instead forever inflating age 13.7 billion years old approximately. Findings converged furnishing cosmological concordance, model lambda cold dark matter, embracing inflationary genesis, dark energy domination growth structure. As cosmological distances surpassed furthest reaches observable locally, alternative standard candles arose filling gaps distance ladder, further refining parameters. Tight bias supernova leveraged calibrating Hubble constant across billions light years, establishing expansion, accelerated around 6 billion years ago, some mysterious dark energy, come domination driving universe expansion faster rate over time. Baryon acoustic oscillations further constrained parameters through imprints density waves, propagated primordial plasma ringing across horizons, scales emergent large-scale structure. Gravitation lensing statistics distortions backgrounds galaxies, galaxy clusters, calibrated densities contents driving dynamics. Microwave backgrounds precise measurements CMB anisotropies, deviations perfection mapped early universe, 13.7 billion years, tracing inflation recombination epoch, furnish definitive anchors calibrate model, predicting observable consequences. According distances measured supernova galaxy clusters throughout space fabric itself, accelerating expansion rate faster according general relativity, dark energy cosmological constant driving apart against resisting mass attracting through gravity. While nature dark energy remains mysterious candidate, proposed Einstein's cosmological constant arising quantum vacuum fluctuations, increasing density vacuum energy proportional expansion volume, or alternative explanations, dynamical dark energy decaying density time. Whatever nature inflation initial breakneck expansion seeded structured later dark energy domination, accelerating expansion forever more diluting galaxies beyond contact. Between within all reside unknown 96% contents driving cosmic evolution through gravitational domination across eons. Yet with modern instruments calibrating model tightening screws comprehension surpasses antique philosophies imagining steady unchanging heavens. Observations frontier observatories arrive refining precision pushing farther. Next generation instruments aims peering over 13 billion light years, calibrating constituents driving cosmic dynamics fine precision. Throughout history transcending concept static cosmos emerged dynamic expanding entity, continuously transforming across time inflation seeded structure, accelerated expansion across horizon. Piece by piece assembling concordance model through accumulating evidence across spectrum wavelengths astronomy, progresses our comprehension far beyond geocentric presumptions. While enigmas persist regarding nature dark contents inflation, initial episodes new instruments promise clarify picture cosmos, emergence earliest moments inflating beyond comprehension. With each new generation edging comprehension, cosmic birth inflation, seeded eons expansion, accelerating fabric spacetime driving apart, visible across deep, forever receding vistas. Future projects calibrating precision, pushing cosmological discovery toward understanding Genesis, fate, ultimate future, driven some mysterious dark gravity, shaping cosmic architecture from beginning end, traversing infinity.